What I want to talk about is how we have electric fields and how they interact with magnetic fields. And so what we're going to do with kind of the rest of the time is go through some of that. Some of it takes some time to practice. And so we're going to practice some of this together with what we're doing, because then you can kind of make sure that you're heading in the right direction. I love this part because we're going to get into the right hand rule and how that works. And so usually like when we're taking quizzes or working on problems, you just kind of see everyone just sort of looking at their hands and all kinds of stuff. So we'll be doing some of that with what we have here. So if you want to have a notebook ready or something like that, you can get that, and we will kind of go through and talk about some of this. A lot of this shows up in the video that we have. Just fell. In the video that we have online, and so you should be able to go back and see some of those things. But like I said, some of it just takes a little bit of kind of time and processing with what we're doing, and so I do want you to do it together here. I need to grab one thing, and then we'll get going. All right. So the whole idea. So right now we've looked at how charges work and kind of looked at fields in general. And what we're going to be looking at in what we're doing here, okay, is how we have magnetic fields and how we have a current or a moving charge interacting in those. And so you know that when you have magnets, you have the North Pole and the South Pole, and the similar poles will repel and opposite poles will come together. And so if you have a north and a north, they will, and you're trying to push them together, there'll be a force there, and you'll feel that pushing apart. If you have a south and a south, those will repel. But if you have a north and a south, that's when your magnets will come together. Well, what happens is when you have a moving charge, when you have a current, you have, it induces a magnetic field around that wire. And if you have that magnetic field in another magnetic field, then it's like two magnets interacting. And so there's kind of two main points to what we're going to talk about here. One, just what happens with the way of inducing that magnetic field around a wire or around a point charge. And then two, what happens when we induce that magnetic field and it's interacting with a fixed magnetic field. And so we'll look at those pieces with what we're doing here. So the first thing I want to talk about is just the idea of what happens with your charges. And so let's say you have a current that is running up a page. So some current here, and we will always talk about this in the way of conventional current. And I'll talk about that in a little bit to what's happening. But conventional current essentially is opposite where the electron flow is. So when we're talking about this, we're talking about our conventional current going up. And if you have a wire that has a current that's running through it, then a magnetic field is induced around it. And so if you were to take, and I'm going to show you this real quick. I also have this in Schoology. If you take and put you put that current in and you have some filings around it, some iron filings, it'll line up in the direction of that magnetic field. And so I have this video on here in our week 2 stuff, videos, etc. And it's just a YouTube video. So if you can see it, you don't need to hear anything on it. So if you can't hear what I'm doing here, that's completely okay. In fact, I'm going to mute. I'm going to make sure this stays muted. Maybe. So you can see on here that he has just a piece of, it's just like plexiglass on there. And then there's a wire that's running through the top. And so that wire will have a current going through there. And it ends up being about 10 amps is what he describes in there. And then he's going to take and put iron filings. And so it's just a really, really fine iron pieces on there. And so he'll shake those on there, and then from there, he'll run a current through it. And when that current runs, the iron filings will respond to that induced magnetic field that's being created. So it just sort of looks like, I don't know, like a little bit of whatever. It's iron filings. It's nothing super fancy. And so he'll put that current through there. When they're on, normally there's no pattern to it, but you can see on here, that he's starting to get some circles formed on there. And when he taps it, you usually have to tap it. It's not going to move without, like, it'll settle into into the magnetic field as long as you tap it a little bit, but it won't overcome that static friction just to go there on its own when you have it on plastic. And so what happens here is after he taps it, you can see that there's circles around there. Oh, come on. There are circles around there that are formed, creating. So here is without the current running through it. It's just a random bit. And then after he taps it, you get the circular pattern that's formed around the wire. And that's responding to the magnetic field that's present because of the current going through that wire. And so what we have and what we're doing, I'll just go ahead and do this so I can go back and forth, is we can figure out what's happening with that field by the way that the current is going and with what we call the right hand rule. So the right hand rule, we'll go back to me. The right hand rule looks like this. And so you'll put your thumb, oh, can you see me? Could you guys see me there or no? Did it go blank? All right, let's try this.
Yeah.
There we go. So what you have with the right hand rule is that your thumb will go in the direction of the current. So in the one that we have, the current is going up the page. And so my thumb would go in the direction of the current there. And then the way that my fingers wrap will be the way that the magnetic field is going. And you have to use your right hand. A couple of years ago, I had somebody and all of his answers were opposite. And I said, show me your right hand rule. And he said, well, I'm left-handed. And I've always, if somebody says right, I just always know to do it with my left. And this isn't one of those cases. It has to be your right hand in order to get what you need in the right direction. So if we have our thumb is going, let's go like this. Our thumb is going in the direction of the current. And so our magnetic field would wrap around and go around the front and come around the back from this picture. So if I have it like this, it would be going around. My magnetic field would be going around like that. I have it up, and you can see that my fingers are wrapping in and around. They're coming up and around and going that way. And so that's how that would be identified when you're talking about the magnetic field or the magnetic field that's induced by the current going through the wire. If I were to take and switch that, and so now if my current were to be going down, well, if my current's going down, my thumb would be going down with the direction of the current, and my fingers would be wrapping around from the back to the front. And so it would look the reverse of what we have, and we would have that drawn like this. And so when you're using your right hand rule, you have to be thoughtful about what's happening and figure out how that goes with your right hand in the direction of the current and then the direction of the magnetic field. Because we have a current going through here, a magnetic field is induced around the edges of it, and that's where we get that response. Now, there's also, unpin this, we'll go back to drawing here. There's also situations that will look a little bit different from that. And that, if we have a current that's coming through here, it's going up, it's going around in a loop, and then it's coming back down here. So let's say you have a setup like this, actually. Well, let me show you a drawing that's not my own. Maybe. Here we go. I'm going to switch that because it's a better drawing than what I have. And so if you have something like this, there's a couple things that you can do. First of all, if we focus on this point right here, this part of the line that's going into the paper, we can use the right hand rule and see what the magnetic field is right around that. And so if we take our thumb's going into the paper, that's a huge hand when I do that, into the paper, and you can see that it is wrapping around in a clockwise direction. And so you can see if you follow the arrows, these are in a clockwise direction. So if we focus just on this area here, because the current is going down into the paper, we have a clockwise direction on our magnetic field. If we focus just on this part over here, and we have our thumb coming up out of the page, we can see that if that's the case, my hand is wrapping in a counterclockwise direction. And if you follow the arrows here, they're pointing in a counterclockwise direction. Well, if this counterclockwise direction continues to come out here, it continues here, it continues there, it continues there. If this clockwise direction continues to come out farther, it continues there and there, and it creates a magnetic field on the inside that looks like this. And so it's a uniform magnetic field on the inside that is pointing. So these lines always point from north to south. And so it would go along that way in that ring. Now the same thing happens if we're looking at something called a solenoid. Oh, one more thing on this. So we can focus on this teeny tiny spot and get the direction that's happening there, get the direction that's happening there, and then break it out to figure out what's happening as a whole. The other thing that happens is we can use a different representation of the right-hand rule in order to figure out the direction of the magnetic field. We can take our fingers, and our fingers become the field, or sorry, the current, and then the thumb points in the direction of the field. And so if I take my fingers here and I wrap in the direction that the current is going around that wire, then my thumb is pointing in the direction of the magnetic field. And so when you have a loop, yes, the first part of the right-hand rule that we looked at can work in this situation where you're going down there, you're coming up here, and if you draw each of those pieces, you can get to that. Or you can say, oh, it's a loop, so now my fingers will represent the direction of the current, so coming around here, and then my thumb will point in the direction of the magnetic field. Now this is for a single coil of wire here. And if we change to something called a solenoid, you have a whole bunch of wires wrapped around. And again, we can take and look at that smaller piece, and we could look at like one of these wires along there. And if we look at one of these wires along here and put our thumb in, you can see that it's coming around in a clockwise direction. And if you look at over here where it's coming out, you can see that then if your thumb is up, that it's wrapping around in a counterclockwise direction. Or if you use that second version of the right-hand rule and put your fingers in the direction that the current's going in that coil and wrap it up around here. So you can see that the current is coming from the back toward the front, and so we'll go from the back toward the front. And our thumb is pointing in the direction of the magnetic field that's induced here. If we were to switch the direction of the current and have it be going backwards, and we would switch the way that goes with the way that we're curving around, our thumb would be pointing in the opposite direction, and it would create the opposite magnetic field of what's being created here. Something else that you can see that's happening in the way that this is going is that you'll have your compass. If you take your compass and put it on anywhere on the field, it'll point along the line of that blue line. So the compass here is right here, and so you can see that the blue line indicating the field is going this way. If we were to set it here, the compass would put this way. If we were to set it on the inside, the compass would push that way. And this will behave as a bar magnet would. This would behave as a bar magnet. So just like one of those with the north and south on it. I don't remember if Mr. Dirks did the monkey hunting demonstration last year where he put up the can and then shot the marble into it. That might have, that sometimes happens and sometimes doesn't. But the way that he has that structured, if he did do that, was by using an electromagnet and a setup with that. And so the electromagnet was wrapped around the monkey part, and then when the marble came through the PVC pipe on there, it broke a piece of foil that was created that had a current going through it. And when that current broke, the electromagnet stopped, and then it dropped from there. And so that's how that was set up, if you happened to see that. The next part that I want to talk about then, so these are just how we get things set up and figuring out where your field might be. And so you may also see other symbols for this. So we focused right now on the different pieces and the way that they worked in what happened with just as we could see it on the page. But sometimes you have things that are going into the page or coming out of the page. So anytime you see an X in a situation is going into the page. If you see a dot, it's coming out of the page. And so in this situation, if I said that I have a current, this can work for current, it can also work for field. And I'll show you that in a minute. So for current, if I had a current going into the page, it would look like this. And if I had my X here going into the page, and I said, well, what's happening to the magnetic field around it? Well, going into the page, I'd take my thumb, right hand rule, put my thumb pointing into the page, and you can see that my fingers wrap around in a clockwise fashion. And so if thumbs into the page, wraps around in a clockwise fashion, would give us an electric or a magnetic field coming around like this. And if I go out a little bit farther, it would still be in that direction. And the farther out we get, the farther apart the lines will become. The farther apart the lines become, you're showing that it's a weaker magnetic field. So the close lines together mean that it's stronger than the lines that are farther apart. So as you move away from the wire that's creating that current, it becomes weaker. Yes. Now, this one is coming out of the page. And so if I take my thumb and have it pointing up, coming out of the page, and I wrap my fingers around, you can see that's going in a counterclockwise direction. And so now I've got my magnetic field is going opposite what it was over here. So anytime you reverse the current, you're reversing the magnetic field as well. So it's coming out here. And again, we're going to get farther away the farther out we get. Farther, why not? Okay, my lines are not perfect, I know that. But that's what we have. And so anytime you see an X, it's going into the page. In the case of a current here, it would just be a singular X or a singular dot representing onto the page. The next thing we'll talk about is talking about what happens in a field. And so sometimes you'll have like a magnetic field where it'll have a whole bunch of X's. And if you see a bunch of X's, that's indicating that you have a field that's going into the page. If you have a bunch of dots in these spots, you would have a field that's coming out of the page. If you think about shooting an arrow, if someone's doing archery and they shoot something away from them, they see the tail feathers of that, and it looks like an X. And if it's coming toward them, they would see the tip of the arrow that looks like a dot. So that's just one way to keep it straight in your mind if you'd like to. So if you have a current that's traveling and inducing a magnetic field, and if that is going through a fixed magnetic field, it's like two magnets interacting and a force is created. And so we have a diagram here that we talk about with this, or a setup, and it looks like this. And so what's happening here is both copper and aluminum, neither of them are going to be magnetic on their own. And so those are good ones. They conduct well, but they're not magnetic. And so they're ones that can work to show this without having other levels of magnets working in with it. And so you have a current that's going through here. It's coming through and it's going around. That current then, because of that, it creates a magnetic field around the aluminum rod here. And because that magnetic field, that rod is in a fixed magnetic field, then those two magnetic fields will interact and create a force on that rod. Now, there's a couple of things that'll happen here. We have, excuse me, another right-hand rule that we use in this situation. And so in this situation, let me see if I printed out that other one. Yes. So if you take and look at this part here, we're going to look at a side version of that in a minute, as if looking down from point B. And you have the current going through here. And if we use our right-hand rule that we know right now, and we put our thumb in the direction of that current, it wraps around from the back and toward the front. So on the back side of it, we've got it going in the same direction of the of the fixed magnetic field, and on the front side of it, when it wraps down, it's going in the opposite direction of our fixed magnetic field. And so if we look at this part, when it's going on the back side, if it's going in the same direction, it's adding to the magnetic field that's there. When it's coming down in the front side, it's going down and it's going opposite. So from the magnetic field that's being created around the rod is pointing down here. And the magnetic field that's the fixed magnetic field is going up. And so those two actually cancel each other out. So over here, you have less of a magnetic field, and over here you have a stronger one. And so it pushes that rod forward. It sort of looks, some people say it sort of looks like a big rubber band slingshot. They're like, and it would shoot off that way. So when we break it down and draw and figure out the fields that are occurring, we can see that because these two would add, this back here would add into the fixed magnetic field, you have a stronger one here and a weaker one here, and the stronger would push into the weaker. Other way we can look at this is with the idea of another right-hand rule. And this other right-hand rule looks like this. This time we have three things in play. We'll have our magnetic field is our fingers. So magnetic field and fingers. And our current will be our thumb. And when you have in your magnetic field and your current, wherever your palm points is the push of the force. And so if we look at this one, our magnetic field is going up from bottom to top, and our direction of our current is going toward the B. And if you put those here, I'm going to move it to what it would be in general. You can see that the push would be in the direction that they have the arrow for the force. And this will show up in lots of different situations as well, frequently using something like this. So let's say that we have this setup and we have X's. So X's indicate that our magnetic field is going into the board. And so take your right hand and your fingers will go into the board. And let's say that we have a current that is going down. Just have a current going down there, down the page. So you'll take your hands and you'll put your fingers so they're going into the board, and then you'll have the current, your thumb, pointing down the page. When this is the situation, your push is over to the right. And so the force that you would have, the force would be to the right. So I'll show you that again. You have your fingers, because it's X's, your fingers will go down into the board. Your current is going down the page like this. And so you have them like this, and then you've got your force that will push over to the right. If I were to change that, and go up, if you had that going, if the current was going up, your fingers would still go into the board. Your thumb would be going up the page, and your push would be to the left. Anytime you flip the current, it ends up being the opposite of what you have. And so this force would be to the left. It would be opposite. Same idea if we were to take and go to the left or the right. Fingers would go into the board. Thumb is pointing to the right here. So my palm is pushing up the page. So my force would be going up the page. And so depending on the situation you have would depend on what that looks like. If these were dots, your fingers would be coming out of the page, and you'd have the opposite of whatever situation you have. All right, let's talk. Last thing, let's talk about a particle and conventional current. So we know that current is a big old line of charges that are moving. And when we talk about current, we are talking about conventional current. And conventional current, I'll get there in a second. Let's take a chart. Well, no, I have to do that first. I don't need my exit yet. Conventional current is talked about as moving from positive to negative. So conventional current is discussed as moving from positive to negative, because at one point when they originally were figuring out things in the way of how all of this worked together, it was believed that it was a positive charge that was moving. And if you have your positive side here and your negative side there, then that positive charge would be repelled by the positive side of the battery and pushed around from positive to negative. When it got over here, it would be drawn into the negative side of the battery. But as time went on, it was found out that it wasn't actually a positive charge that was creating that current. In fact, it was the movement of electrons, and electrons have a negative charge. So the flow of electrons, they're going in the opposite direction of what we talk about as current, because electrons are negative and they're repelled by the negative side and then drawn into the positive side. And so at that point, scientists, the scientific community, had to come to a figuring out, because they said, well, everything that we've talked about, we've always gone positive to negative. Do we really want to change all of that? And they said, well, maybe not. Let's do this. Let's just keep it like it is and just say that we know it goes in the opposite direction. And so that's what they landed on. A little TOK thought, like what went into figuring out that that was the best idea. And at the time, it probably made a lot of sense, because they could just keep going on and saying and doing the things that they normally did. But now at this point, it's like, well, why didn't they just switch it back then? Because then we could just use it as it is. But here we are, scientific community still discusses, and we say conventional current a conventional current goes from positive to negative, even though the flow of electrons goes from negative to positive. I know that's goofy, and it's something that we just kind of have to stick into our minds for what we're doing. And again, if we could turn back time and go back to that scientific community and be like, time out, can you just switch it now? It'll make it easier for everybody moving forward. That'd be amazing. We can't, so we're just going to stick it with this. And I get it. Nobody wants to be the one to be like, it's time to change. So conventional current, we talk about, we draw, we just keep in the idea as positive to negative, even though we know the flow of electrons is opposite that. I'm going to erase this because this is how it plays into the fields that we're doing here. So I'm going to go ahead and put my X's back on here. And we've talked so far about the way that current in a wire behaves within this. But the other thing that happens is we can have this in a particle. And so let's say I have a positive charge of some part of some sort that's traveling through a magnetic field. And so this charge will still create a magnetic field. It'll induce a magnetic field around it. And I can still figure out the direction of what I'm doing by using the right hand rule. If the charge is positive, conventional current points from positive to negative. And so this would behave as conventional current. And so we would just do this as normal. So we'd say if it behaves as conventional current, and we would just use the right hand rule. Standard right hand rule. So we would say, well, our magnetic field is going into the page. Our thumb, the direction of the charge, is going up the page. And so we would just do exactly what we did when we're talking about this being in a wire. And so our push would be over to the left, so our force would be over to the left. Now here's the deal. If it is a negative charge, likes to mess with us. If it's negative, it's going in the direction of electron flow. and that's opposite conventional current. And so if it is a negative charge, therefore it's moving whatever the electron flow is. If this is moving this way, it means that conventional current then would be notated as in the opposite direction. So when you do that, your thumb points opposite of negative motion. And so this is the same situation that we just had. We have our magnetic field going into the page. We have our electron moving up the page. So if it were anything else, we would say, well, oh, hey, a magnetic field into the page, electron moving up the page, cool, and it would go that way. However, because the electron's moving up the page, that's the opposite direction of conventional current. So our fingers still stay in, but we flip our direction of our thumb going down. And so the force would be over to the right in this situation. The force would be to the right. The only time that you have to switch that is when you have a negative particle. If it's a current or if it's a positive charge, the right-hand rule stays as is. If it is an electron or some other particle with a negative charge, if they're talking about this is a particle with a negative charge, electron, however it goes, then your conventional current would be opposite of the electron flow. So you would flip that down, and then you would have the opposite in the force. And so however you want to remember that, however you want to work through that, that's what we're looking at on this. Two more things. Thing one, we do have some equations here. And I go into all of this in some more detail in the video, so I'd still suggest watching it. But we have two equations. To calculate the magnitude of the force. It's directionally, you'll need to use the right-hand rule with what you're doing. But you have B, I, L, sine theta with what's happening here. B is your magnetic field. And it's measured in Teslas. I is your current, measured in amps. L is the length of the wire. And it's measured in meters. Sine theta, all of these, if your magnetic field and your current are, and your current and wire are perpendicular to each other, then sine theta ends up just being 1. If it's 0, sine theta ends up being 1, and you're fine. If they are not in, if there's an angle to them, then you end up with a lower amount. And I go into all of that in the video, so I'd watch the video on that one. The other part that you have, if it's a particle, you have B times the charge times the velocity of the charge, sine theta. And so you have charge. This is still your magnetic field. This is your charge, velocity of that particle. And that's in meters per second. And the charge is in coulombs. And so if you break down and look at the units, you have your magnetic field in Teslas for B. For here, current, you have amps is coulombs per second. And then you would have your length in meters. Here you have your charge of coulombs, but then you have meters per second. And so you still have all of the same units in order to get to that force. And like I said, there's some diagrams that I talked through in the video that'll help you out with that. I think I also have the PowerPoint up there. If I don't, I will get that taken care of as well. Let me just see. Just to make sure. Yep, the PowerPoint is on here and it talks about that in there. And then the textbook pages are listed here as well. So, things to keep in mind. you just have your practice problems on this. You'll be quizzed on it next week. I don't have a quiz on it this week. We'll add in a little bit more next week, and then we'll quiz on both. And then we will keep moving forward on each of those. So I'm going to be done presenting here. I just threw a whole lot at you, but it's something that I wanted to talk about while we were all here, as opposed to just hoping that you watched it. I wanted you to practice it with me. Any questions that you have on any of this stuff that we've been looking at? Biggest thing is that you're keeping in mind that a moving current will induce a magnetic field. And so because of that, sometimes it's just figuring out what that magnetic field is. And sometimes it's figuring out how that induced magnetic field operates and interacts with a fixed magnetic field. For any of those, we have the right-hand rule, different variations of the right-hand rule. And so be comfortable being able to draw what's happening, being able to discuss what's happening, and being able to calculate what's happening. And then we'll keep moving from there. So if there aren't any other questions, I'll hang on here if anyone has individual questions. Other than that, enjoy the rest of your week. Give lots of turkey high fives this weekend, and enjoy your 4 days. If you're behind on anything, whether it's in this class or another one, please, please, please take time to get yourself caught up and take a deep breath and have a wonderful weekend. So thank you. We'll see you all later. Bye-bye.